Okay, so for our example 3, the reaction that's shown here is a little bit more complicated than what we've seen in reactions for our examples 1 and 2, where we talked about SN1 and SN2 reactions and also the electrophilic aromatic substitution reaction. And so in this case, we are reacting substituted benzaldehydes with an ylide in order to form an oxirane ring through the zwitterion intermediate. And so what the question is the mechanism or the reaction scheme shown here consistent with the experimental data obtained from the Hammett plot? So this Hammett plot was developed where they looked at the rate constant for the reaction with benzaldehyde with specific substituents in the aromatic ring versus the unsubstituted one, and they plotted that against our sigma value. And you can see that now we have a fairly moderate slope, which is positive. So the question is, if we look at this mechanism, can we figure out where we're going to have charge change, which is consistent with a positive slope of moderate value? So if we remember, if we have a Hammett plot that has a positive slope, that is telling us that electron withdrawing groups will speed up the reaction and electron donating groups will slow down the reaction. And that this influence is going to take place in the rate determining step, which is the formation of this zwitterion by reaction of the ylide with the benzaldehyde. And so our ylide is formed in a pre-equilibrium where we have some base which is going to pull off this proton to give a carbanion, which is called an ylide, as the sulfonium ion has a positive charge, so we have a zwitterion structure here. And we can think about this zwitterion structure where the negative charge density is going to react at the carbonyl to open up the pi bond. And so is this mechanism consistent with this positive slope for our Hammett plot? Or more or less, if we have electron withdrawing groups on that benzaldehyde, will that help this reaction take place? So let's draw out the transition state structure for the reaction of the ylide with our substituted benzaldehydes, and see if we can think about what the transition state structure is going to look like. So we're going to get nucleophilic attack, and so our ylide is going to act as the nucleophile, and our benzaldehyde is going to act as the electrophile, so we need to keep that in mind. And so when we do this reaction, we're going to start with the point of negative charge, and we're going to use our curved arrows. It's going to react at the carbonyl, and we are going to open up the pi bond, the carbon-oxygen pi bond. And so we can think about if this is the rate determining step, so this would be our slow step, And this would be where the substituents would take, the interaction of the substituents or the influence of the substituent will take place if this is true. And so is this consistent with a Hammett plot where we have a rho value of plus 2.5? Okay, so we can start to draw out the transition state structure, and we can think about where we might be able to utilize or visualize the influence of those substituents on the aromatic ring of the benzaldehyde. So we can think about, we're going to break the carbon oxygen pi bond, and we're going to start to form the carbon-carbon single bond from our ylide. And so we're going to have a delta minus on the carbon of the ylide and a delta minus on the oxygen of the carbonyl. But what about the carbon of the benzaldehyde? What has happened to the charge at that carbon? And is that difference in charge consistent with this slope for our Hammett plot of positive 2.5? So it turns out that this is indeed consistent with the Hammett plot, the rate determining step as shown, and the transition state structure as drawn. And this is because that we know that for our carbonyls, these types of compounds are highly polarized in the ground state. And so we know that the reason why carbonyls, aldehydes, act as electrophiles is because they have significant positive charge on the carbon of the carbonyl. So when we go from our starting material to the transition state, what have we done to the positive charge on the carbonyl? So when we think about the amount of positive charge that's here, we have diminished the amount of positive charge in the transition state. And so really what we're saying here is that the electron withdrawing groups will destabilize the benzaldehyde. And if the benzaldehyde starting material is destabilized, the reaction will be faster with the ylide. And this is consistent with the mechanism for the reaction as shown on the previous slide. So in this case, the electron withdrawing groups speed up the reaction because we have a decrease of positive charge in the transition state. And so this allows the electron withdrawing groups to destabilize the benzaldehyde and increase the rate constant for the reaction, leading to a positive slope which equals 2.5.